In this module, we will study fluid flow and the application of numerical methods to fluid flow phenomenon.
In the last video, we set up and solved a 3D bathroom faucet example. We will now examine the results of the 3D CFD analysis of the bathroom faucet. Recall that we created a two-scenario design study. The first CFD scenario had a 1.5 GPM cold water inlet. The second scenario, scenario 2, had a 1.0 GPM volumetric flow rate at the cold water inlet. We are ready to post-process these two CFD solutions to understand more about our faucet design. So now the analysis completed. If we look, we can see the convergence plot shows this scenario has been run. We can do the same thing down here with scenario 2 and see that everything is converged. You see the flat lines and the convergence monitor there. So let's go back to scenario 1. We're going to set up a better view so we can see some of these results. Close that output bar. We can always open it up again by clicking that button. And then since we're not really interested in the copper body, we've hidden that, so we just have the water part and the mixing valve part. So let's look at some results. So we were plotting static pressure as we were running the solution. Let's change the units of that to Pascal. You can see the pressures are higher where it has to impinge on this mixing valve there. And then we can see the inlet pressures for both the cold and hot water as well. So that would indicate the pressure drop in this faucet. You can also plot the temperature, since that's something that we wanted to study. Let's change the units of temperature to Fahrenheit. So there's our 120 degree F hot water inlet and our 45 degree F cold water inlet. One thing that we can do in the global results, in any results really, we can kind of hover our mouse over the model. You can see down in this bottom bar down here that the values are changing. It shows you the location where you are, the part that it's hovering over, element ID, and then the value. So you can see that our outlet faucet pipe is going from the high 70 degrees Fahrenheit, nearly 80 degrees Fahrenheit. As we get over here to the higher temperatures, it's over 102. So this has a pretty wide range. That's about 20 degrees delta T in that outlet pipe. So we're definitely looking at making some kind of design change to this model. Another thing we can do is we can create path lines or particle traces. So in this model, let's look at creating some traces that end up here at the outlet. And it'll fill in how they got there from the inlets. So we're going to choose a seed type that is circular. You could have a point, a line, a ring, a rectangular arrangement. We can choose a region, or we actually can key in values, but we're going to choose circular since our exit pipe is circular. Then we'll look at a hexagon pattern. We hit the plus. We click in the middle of the pipe and out here near the edge. And that should have created some traces. In order to see those, let's look at outlines for these two parts. And here you can see now the traces where all of those particles came from. And we can animate those traces. Back here to the traces and we hit animate. Let's make this about 25 seconds. And we can see where the individual traces, and track those a little bit better, and see where some of the recirculation regions are and how the different baffles move the traces around. So we'll stop that animation, and then we can go to the end and see those traces again. Cutting planes are 2D slices through the 3D volumes. These planes can be oriented in any direction. You can right-click on the plane and choose X, Y, or Z. You can also use the mouse to grab the arrows or curves of the plane to drag the plane anywhere you want. You can edit the planes, change the result that is displayed on the plane, change the appearance of the plane, and change the location of the plane. Let's turn that off. And let's choose to look at the results task. I'm going to look at creating a cutting plane. So cutting planes, let's just add a cutting plane here. So you can see this cutting plane slices through the middle of the model. We want that plane to be a Y plane. So now you can see the little Y plane there, and we can take one of these arrows and grab that handle and just drag it to the exit, or nearly to the exit. And there what we're going to do is we're going to look at the bulk values of the temperature there. So we're going to choose temperature, and let's choose Fahrenheit for the units, and we can calculate the bulk value at the exit there. So the bulk temperature at the exit is actually 87 degrees Fahrenheit. So we put 120 degrees Fahrenheit in the inlet, hot inlet, and the cold inlet had 45 degrees. And that bulk temperature is 87 degrees. A bulk value is an average value that's weighted. It's weighted by the mass flow that's coming through that opening. So we're going to save this information as a CSV file in here. This is the outlet bulk temperature. We're also going to create a summary image. So this image that we have here, this plane is going to become an image when we look at the design in the decision center. Let's also make this cutting plane a summary plane. So again, that plane there cutting plane that we've put at the exit will appear in the decision center for both of our scenarios and for any design that we put in the design study bar. So let's also go ahead and create an XY plot, and we're going to look at the plot of the temperature. We'll add some points. So we can start clicking down here where the high temperature is, and we'll just click some points across the diameter of that outlet pipe, and then we can plot those points. So between each of the points we picked, some points are interpolated, and the default is to have 20 points, 20 divisions per segment. So there's 20 divisions between each of the points that we just selected. And we can create a summary plot of this data. We can save the data in a CSV file. We can also save the image as a bitmapped image. And finally, let's save the points. This is our exit plane XY of temperature. Save those points, and then we can use those points again. Let's create another plane, and we'll make this plane be a Z plane. Again, we can see that Z plane there. We're going to grab the handle of that Z plane, just drag it up to be about halfway through the two water inlets. See, if it's a Z plane, it's going to be normal to this Z axis. The outlet plane we had was a Y plane, so it's normal to the Y axis. Let's make the plane be transparent so we can see it a little better. And we're going to add velocity vectors to that plane. And this little icon here lets us set up the vectors. I can change the size of those vectors by sliding this slider, and I can increase the number of vectors on the plane by sliding this down. And you can see that those vectors sort of match up with what we see in the particle traces, where some of the flow is deflected upward. These vectors are showing, but most of it's coming down around the outside of that divider. And one of the things that we can see is that the divider actually has quite a bit of space between the divider and the inside of the pipe wall. So one of the design changes that we might want to make is to increase the diameter of that divider so that we can force some of the flow to mix before it gets to that outlet. Okay, now let's look at the wall calculator. So in the wall calculator, we can calculate the average force, pressure, temperature, heat flux. So let's choose, we're going to choose, let's hide the water part so that we can choose the surfaces, and we can choose it by volume. So we can choose all the surfaces on that divider part, and we can look at the forces, the pressure, the temperature. We might want to know the heat flux just to understand how much heat is actually being conducted into the divider. And then we hit calculate, and then for each of the surfaces on that model, we get the area of the surface, the average pressure on that surface, the average force in the x direction, y direction, and z direction, and then the center of force for those different forces, the average temperature, and the heat flux. And then for the entire volume or part, we get a sum of all of those. So this is the total surface area of that divider. This is the total force in the x direction. So this is the x direction. So there's actually, because we have more hot water coming in, it's going to tend to push the divider towards the cold water inlet. And then the total y force. So the y force is actually acting opposite, which makes sense that it's coming out the outlet. And then there's a z force acting down on the divider part because of all those baffles. And we get the center of force, and we also see the total heat flux for that part. Another interesting post-processing quantity is the isovolumes. So if we create an isovolume, it's just an isovolume of the temperature. This shows the volume. There's an actual value, so we'll open this edit up. So the volume that's created here is in the temperature range of 82.5 to 120 degrees F. We can slide this around and see where maybe the 100-degree temperature is. So we can slide that value, or maybe we want to see where the hottest temperatures are. So this volume represents the volume of those hottest temperatures. So now let's move to the decision center. The first thing we want to do is to update all of the values for the different summary images and planes that we set up. You can see in this summary image, we can see the two scenarios. This is scenario 1, and this is scenario 2. And we can look at these two images. Here, there's image 1. And we can slide the slider back and forth to see those images. And here's image 2. This was the ISO volume, so you can see how the hot water has creeped further along into the space between the divider and the inlet pipe. We can go to the planes, and we can look at plane 1. This was the exit plane. So these were the two scenarios we were looking at. These are the two volume flow rates. You can see that the volume flow rate for scenario 2 is less because we had less cold water coming in. These values are negative, indicating that the flow is leaving the pipe at this location. we can compare the temperatures, and we'll change that units to Fahrenheit. So in the first scenario where we had 150 GPM of cold water, we have about 88 degrees Fahrenheit. And then when we reduce that to 100 degrees, we had about 95 degrees Fahrenheit. And this was the other plane. And then this was our scenario.
This concludes our video on 3D CFD post-processing of the results.